Good morning, students. So, in last class we discussed up to in the 8th unit adiabatic process. Now we pass on to the third process, that is the isobaric process. So, thermodynamic process that occurs at a constant pressure. That is, even though the pressure is a constant in this process, but the temperature, volume, and the internal energy are not constant. So, you know that if it goes for the ideal gas equation, one must be a constant. So, here which has to be a constant means pressure is a constant. So, from the ideal gas equation, we have V is equal to mu R P into T. So, here mu R P is nothing but a constant. So, isobaric process, the temperature is directly proportional to the V volume. So, that is a isobaric process. So, this implies that the isobaric process VT graph is straight line passing through the origin. If a gas goes from the state of, that is from initial state to the final state, so VITI goes to VFTF at a constant pressure, the system satisfies the following equation. That is, we are finally getting that we are taking that the final has to be on one side and the initial values on the another side. So it will be, we are getting that TF by VF is equal to TI by VI. So what are the examples for this isobaric process is when the gas is heated and pushes down the piston, so that it exerts a force equivalent to the atmospheric pressure plus the force due to the gravity. So you know that if you are giving the pressure in the upward side means there will be a downward force is also acting. So both will be, the opposing force is also there. So and that is known, this process is known as an isobaric. So that is given here through the diagram. Okay, and the second example is nothing but most of the cooking process in our kitchen is a isobaric process. When the food is cooked in an open vessel, the pressure above the food is always at a atmospheric pressure. So this is a example for an isobaric process. So the PV diagram for an isobaric process is a horizontal line parallel to the volume axis. Okay, so that is figure 0.8. See this one, this diagram only given as a figure 8.35. So here the PV diagram for the isobaric process, here we are taking the two volumes, that is for the final stage and also for the initial stage how the pressure will be. Okay, so here also we are getting the same thing. So this is the work done in an isobaric process is nothing but pressure into the volume, that is a derivative of the volume. So for that volume we are taken that the initial state and also the final state. So in isobaric process the pressure is a constant, so P becomes what? Out of the integral. If it is a constant we are taking as a out and only we are derivating the volume. So we will get an the derivation after the integral. So we are substituting the limits, upper limit minus lower limit. So we are getting that VF minus VI, that is the change in volume, so that mentioned by del V. So here we are getting that del V is nothing but the change in volume. So if del V is negative, what is the meaning of the work done also negative? So if it implies that the work done is on the gas. If the del V is positive means work done is also positive. That implies that the work done is by the gas. Okay. So what the one is work done on the gas. If it is a negative means work done on the gas. If it is positive means work done by the gas. So the work has to be done by the gas. The work has to be done on the gas. So two different things you are having. If it is a negative, the work has to be done on the gas. If it is a positive means the work done is by the gas. So that the work has to be done only by the gas, then only you are getting a positive volume. Understood, students? So the equation can also be written as through the ideal gas equation, that is PV is equal to mu RT. So if you are taking V only, take the other pressure into the another side. So you are getting V is equal to mu RT by P. So you are substituting this value in the work done means you are getting 1 minus Ti by Tf, that is mu RTF is equal into 1 minus Ti by Tf. So PV diagram or under the isobaric curve is equal to the work done in isobaric process. So that diagram is given here. So this is the first law of thermodynamics for isobaric process. Okay, so that is nothing but del U is equal to Q minus P del V. So this is your final equation for isobaric process. And next we pass on to the isochoric process. Isobaric process is also a thermodynamic process. Here the volume of the system is taken as a constant. So please you have to understand what has to be taken as a constant for the each process. That is a very important one. If you are taking the isobaric, the pressure has to be a constant. If you are going for the isochoric, then the volume has to be a constant, but pressure, temperature and the internal energy to be a changing one. So it's a variable. The pressure volume graph for an isobaric process is a vertical one. So see here how we are getting the PV diagram for the pressure, because here volume is a constant, so we are getting on the vertical line. In isobaric you are using that volume has to be a variable one and pressure has to be a constant, so you are getting a horizontal line, but here pressure is changing, so we are getting a horizontal line as a PV diagram. So isobaric process is increased with pressure and decreased with pressure. So what is the final equation? Same, Pi by Ti is equal to Pf by Tf. So isobaric process del V is equal to 0. So if del V is 0, what happened? The work done is also 0. So the first law becomes del U is equal to 0. So it implies that the heat supplied is used only the internal energy. As a result, the temperature increases, the pressure also increases. Okay, so if you are increasing the temperature, pressure also getting increases. Understood how it will be a initial and also in the final stage. That is, suppose a system loses a heat to the surroundings through the conducting walls by keeping the volume constant, then its internal energy decreases. What happened finally? The temperature also increases and decreases, and the pressure also decreases. Both will decrease. For example, for this one, when food is cooked by closing with a lid, if you are for the isobaric it is an open one, no. For the isochoric, the food is cooked with a closed vessel. Okay, so closed with the lid. So that is the best example for the isobaric process. And when a food is being cooked in this closed position, after a certain time you can observe this lid is being pushed upwards. Now if you are cooking the food, you know that, no, if the rice has to be boiled, if it comes out, the upward lid has to be open automatically, okay, through the water stream. So this is because when the lid is closed, the volume is kept constant. As the continuous heat is applied, the pressure increases, so the water stream tries to push the lid upwards. So that is the best example for the isochloric. And the one more example is given, that is in automobiles, the petrol engines undergoes a 4 process. That is, a piston is adiabatically compressed, and the second process, the volume of air fuel is mixture with the kept with the constant, and the heat is being added. As a result, the temperature and pressure are increased. So isobaric process, for a third stroke there will be an adiabatic expansion, and fourth stroke again isobaric process by keeping the piston immovable. So these are the good examples for the isobaric process. And next we pass on to the cyclic process. This is a thermodynamic process in which the thermodynamic system returns to the initial state after undergoing a series of changes. So since the system becomes back to the initial state, the change in internal energy is 0. So what is the meaning of it? When the heat flow into the system and out of the system, so from the first law of thermodynamics, the heat transfer of the system must be equal to the work done by the gas. So what amount of heat is going, or that means it take in or it going out, that must be equal to the work done by the gas. So that is a high cyclic process. So Q net is nothing but Q in minus Q out, that is equal to W. PV diagram for the cyclic process. In the cyclic process, the PV diagram is a closed curve. So gas undergo a cyclic process in which it returns the initial stage after the expansion and the compression. So these are the diagram for the cyclic process. When work done by the gas during the expansion means a volume 1 to volume 2, that is change in volume, that's equal to the area of the graph, that is CBA. So this area must be equal to the change in volume. And the next one also is given as ADC. So the change in volume has to be taken out. And next, the work done on the gas during the compression means volume 2 to volume 1, that is here also the change in volume, but the area will be equal unto ADC. Work done is W1 minus W2, that is the green shaded area is the work done for this PV diagram. Okay, so here the net work done during the cyclic process show the above is not zero. So in general the net work done can be positive or negative. If it is positive, work done by the system is greater than work done on the system. If it is a negative one, work done by the system is less than work done on the system. So this is the difference between the PV diagram and the cyclic process. Okay, so cyclic process, adiabatic and isobaric are the very important one. So you have to read and you have to know the differentiation of all these process, which has to be taken as a constant and which has to be taken as a changing in as a variable. Okay, next we pass on to the heat engine. In the modern technological world, the role of automobile engines plays a vital role in the transportation. So in motorbikes and cars, there are the engines which takes in the petrol, diesel as an input and do work for rotating the wheels. So most of these automobiles engines have the efficiency not greater than 40%. So the second law of thermodynamics puts a fundamental restriction on the efficiency of engines. So therefore understanding the heat engines is very important. First term is a reservoir. What is that reservoir? It is defined as a thermodynamic system which is a very large heat capacity. By taking in heat from the reservoir or giving heat to the reservoir's temperature does not change. So it's a very important one. It's a heat capacity, very large heat capacity. So it will take and also give the heat to the reservoirs. That example, if you are pouring a tumbler of hot water into the lake, will not increase temperature of the lake. That means it will not increase the temperature of the lake. Here the lake can be treated as a reservoir. So like that, when a hot cup of coffee attains equilibrium with the open atmosphere, the temperature of atmosphere will not appreciably change. The atmosphere can be taken as a reservoir. That means if you are giving any small heat, that is a small change in the heat, that would not change a bigger thing in the reservoir. We can define that heat engine as, heat engine is a device which takes heat as an input and converts that heat into a work by undergoing a cyclic process. So three parts it will have: hot reservoir, working substance and cold reservoir. The schematic diagram for this engine: hot reservoir to heat engine and then cold reservoir. Okay, hot reservoir, it supplies the heat to the engine. It always maintain in a high temperature. Working substance is like a gas or the water which converts the heat into a work. So an example given for the heat engine is steam engine. In olden days, steam engines were used to drive the trains. So the working substance which absorbs the heat from the burning of coal, which converts the heat, that means the water, into a steam. This steam does the work by rotating the wheels of the train. Okay, then only the train can move. Okay, so here the work is nothing but to change the heat as a work. Cold reservoir is a sink. The heat engine ejects some amount of heat that into the cold reservoir after doing the work. So it's maintained as a very low temperature. Automobile engine, the cold reservoir is in the surroundings at room temperature. So the automobiles ejects heat to these surroundings through a silencer. The heat engine works in a cyclic process. So after a cyclic process, it returns to the same state. So the heat engine returns to the same state after ejects the heat, the change in internal energy. So what happens if it takes the heat and it changes as like a work, and then it gives whatever the heat used. So no change has to be taken place in the heat. So the internal energy will becomes what? Zero. So the efficiency of heat engine is defined as the ratio of work done to the heat absorbed in a cyclic process. So the working substance absorbs heat, that is a QH units from the source, and reject QL, that is low heat units to the sink after doing the work done unit. So that is given as in the diagram. After the work first it gives a heat to a engine, that is as a work, and after finishing the work it gives again the heat in the form of a cold to the cold reservoir. So no change has to be taken place in the heat. So we can write that input heat worked in plus ejected heat, that is QH is equal to W plus QL, when W is equal to QH minus QL. So efficiency is nothing but eta. So output by input, that is W by QH equal to QH minus QL by QH. So output by input, that is W by QH is equal to 1 minus QL by QH. Here QL, QH and W are taken as a positive. The sign convention followed in the expression. When the load, that is a QL, the cold reservoir is lesser than the heated one, the efficiency always less than 1. It implies the heat observed is not completely converted as a work. So the second law of thermodynamics placed fundamental restrictions on converting the heat completely into work. So we can say that heat engine statement of second law of thermodynamics, this is also called as a Kelvin-Planck's statement. Okay, understood students? So this Kelvin-Planck statement is nothing but it is impossible to construct a heat engine that operates in a cycle whose sole effect is convert to the heat completely into the work. This implies that no heat engine in the universe can have the 100% of efficiency. Understood? So that is a Kelvin-Planck statement. Understood what is given in this lesson, children? So what are the different process and what is a heat engine?